Hi everyone, and welcome to this series of solving PEO technical exam questions. And we are solving questions from the Electrical A5 Electronics course. So this question is a second MOSFET question, but this is different than the previous one, which was about DC bias. This is about DC bias as well as AC analysis. Okay, so before we go through the question, let's just have some sort of a background to understand how to deal with such questions. So similar to the BGT transistors, then we need to analyze the circuit in the DC analysis. And then we have to know the model, draw the model, and then find the gain, input resistance, output resistance, whatever is required in the question. So the model for the transistor, basically the MOSFET, is we have two models. The first one, when we ignore the output resistance, and we have here GM, which is equal to K, a constant, times VGS minus VT, and this VGS will bring it from the DC analysis. It's always also equal to root of 2K ID, and also ID we can bring it from the basically the DC analysis. Sometimes if lambda is not actually equal to 0, which will lead that will be an open circuit. So if lambda has a definite value, then basically we include R0, and R0 here is equal to VA divided by ID. So let's see the question here. So basically in the following stage, common source amplifier circuit. So this is an amplifier circuit, okay? And this amplifier circuit, we have certain quantities. We have V, the threshold value is 1 volt, K, which is 4 milliampere volt squared, and lambda is equal to 0. If lambda is equal to 0, so as per this, if lambda is equal to 0, this will be an open circuit. So we will using this, basically this model, because R0 will be infinity, an open circuit. Okay, so the first part here is basically a DC bias question. And in the DC bias question, as we know, we did before, we basically all the capacitor will be an open circuit. And we will disconnect the AC source from the circuit. We also disconnect the load from the circuit. So if this is open circuit and this is open circuit, basically that will be our transistor model. So we have here VDD is given to us as 15 volts. So this is 15 volt. And we have here all these resistors connected. This is your RG2, this is your RG1, and also this is 15 volt. We also given ID here is given to us is equal to 0.5 milliamp. And VS, so this is VS, the voltage between the source to the ground. So your VS is equal to 3.5 volt. VD, the voltage between the drain to the ground, VD is equal to 6 volt. Now, so ID is given to you, VD, VS is given to you, and we want to find the resistors, all the resistors, RG1, RG2, and RD and RS. So that is the first requirement in the question. And always this is an NMOS transistor, okay? It's here N channel MOSFET. So these are the conditions that we want to watch if the transistors is in the saturation region. So start part A. Okay? In part A, now I know VD is equal to 6 volt. So the potential from here to the ground is 6 volt. And here's 15. So 15 minus 6 divided by the resistance RD This basically is equal to your ID, which is equal to 0.5 times 10 to minus 3 milliamp, 0.5 milliamps. So your RD can find directly 15 minus 6 divided by 0.5 times 10 to minus 3, and this is equal to 18 kilo ohm. Same thing for RS. I know VS, and ID will, because the current here, as we know it, is equal to 0. The current here, I, is equal to 0. So this is also your ID. So this is equal to also 0.5. So we'll do exactly the same thing. Your ID, which is equal to 0.5 times 10 to minus 3, is equal to 3.5 minus 0 divided by RS. And from this, you can find your RS is equal to 3.5 divided by 0.5 times 10 to minus 3, and this is equal to 7 kilo ohm. So we found RS, we found RD. Now, we want to find RG1 and RG2. Okay. Now, here we will assume the transistor in saturation region. Okay. So assume saturation. So if it is saturation region, basically you will use this formula. Now, lambda is equal to 0, so this is what equal to 0. So your ID is basically equal to 1/2 times K times VGS minus the threshold value. And this is equal to 1/2. K is given to you as 4 times your VGS, which we don't know. This is our unknown, minus the threshold value is equal to 1 volt square. This is square, of course. And this is equal to your 0.5 times 10 to minus 3. This is your basically your current. Now, again, as I mentioned before, this is also 4 milliamps. So this will be here also 10 to minus 3. So these 10 minus 3 will cancel with each other. Now we have a quadratic equation. So if we open the brackets, we will have 4 VGS squared minus 8 VGS plus 4 equal to 1, or 4 VGS squared minus 8 VGS plus 3, this is equal to 0. Now we need to solve for VGS, so we use the quadratic formula. So VGS is equal to minus 8, this is 8, this becomes plus 8, plus minus square root of b squared, which is here will be minus 8 squared, minus 4 times a, which is 4 times 3, divided by 2a, which is 8. And this will give me two answers, 1.5 or 0.5 volt. Now, for saturation, VGS has to be more than VT. There are two conditions. VDS has to be more than VGS minus VT, and VGS has to be more than VT. Now, this condition is basically common between the triode region and the saturation region. So that is excluded because we know VT is equal to 1 volt. Okay, so my VGS will be equal to 1.5 volt. Okay, so I know now the voltage between this is your drain, this is your source, and this is your gate. So your VGS, the voltage between G and S, is equal to actually 1.5 volt. So let me redraw the circuit quickly here. Okay, so this is my transistor now, and I will concentrate on RG1 and RG2. So this is your 15 volt, this is your RG1, and this is your RG2, and these are basically grounded. Okay, so here we will have our VG. Now, VG, because RG1 and RG2, they are in series, because remember, the current here is equal to 0. So we can apply voltage division. RG1 and RG2, they are basically in series. So voltage division is applied here. So from this, you can see that your VG is equal to the 15 volt times RG2 over RG1 plus RG2. This voltage VG is equal to the VGS plus the VS. So this is equal to VGS plus VS, which is equal to the VGS we found it as 1.5 plus the VS is already given to you as 3.5 volt, which is equal to 5 volt. Okay. So now we have an equation with two unknowns, okay? And so you have RG2 over RG1 plus RG2 equal to 5 over 15, 5 over 15, or equal to 1 over 3. So that 3RG2 equal to RG1 plus RG2. And from this, you can say that your RG1 is equal to 2RG2. So that is the criteria for RG1 and RG2. Now, at that part, we have no other information to find a specific value for RG1 and RG2. So you can say that select RG1 to be, let's say, any value, 10 kilo ohm, then your RG2 will equal to 5 kilo ohm. Because there is no any other criteria is imposed on this. So with this, we are done with the first part. Now let's go for the second part, which is the AC analysis. Now, but before that, I forgot one important point that we need also to check. Remember, we assume that the system is in basically saturation region. Okay. Now VDS is equal to 6 minus 3.6 minus 3.5, which is 2.5 volt. This is VD, this is DS, VDS. 6 minus 3.5 is 2.5 volt. This is basically greater than VGS, which we found it as 1.5, minus VT, which is minus 0.5. So actually, yes, the transistor is basically in saturation region. Now, let's go and try to solve the AC analysis. Now, here in the AC analysis, it says that assume that the equivalent resistance Rn is equal to 1.67 mega ohm. R1 is given to you. RL, the load resistance, is given to you. We want to find the voltage gain, which is V out Vn. What is the V out over Vn? What is the voltage gain? Okay. So to do that, we need first to draw the circuit for the AC analysis. And here the capacitors will be short circuit, and we will remove the DC bias. When we do the AC analysis, we will remove the DC bias. So our model now, since lambda is equal to 0, so I will not include R out in the model. So that is basically the model of the transistor. We will have our GM times VGS. And this is connected. So this is your transistor here. So this is connected from the source with RS. So this is your RS. And then we will have here the open circuit. This is your G, okay? And this is your drain, and this is your S, okay? So here, this is your VGS here, VGS. And then we will have these two resistors in parallel, RG1 and RG2, because I short circuit the supply. So I will have here RG1, RG2, and these two are basically in parallel, then I will have here R1, and I will have here the supply, which is VN. And then in the output from the drain, we will have RL, this will be short circuit, and RD short circuit as well. So we will have here RD grounded in parallel with basically your RL. And your output is across RL, so this is your V. So that is the small signal model of my transistor. Okay, now we need to find VGS and we need to find GM to be able to find the gain. So what is your VGS? VGS basically here using voltage division is your input voltage times the equivalent resistance of these two, okay, as a voltage division with R1, okay? So this will be like RG1 in parallel with RG2 divided by RG1 parallel with RG2. That is the equivalent of this, okay, plus R1. So all of this will be one resistance in series with R1. So basically, our voltage division times your VN. Okay. Now, what is RG1 in parallel with RG2? How to find this? Okay. Now, we will not use the previous results because here they give us basically a condition. It tells you that your Rn is 1.67 mega ohm. Now, what is your Rn? It shows here, this is the resistance. Now, when you look here, so you look from this side, this is your Rn. What you see RG1 in parallel with RG2. That is your Rn. Okay? Because everything is open circuit, that is. So this will be 1.67 times 10 to power 6 divided by 1.67 times 10 to power 6, which is this, the parallel combination, plus R1. What is R1? R1 is given to you as 100 times 10 to power 5 times Vn. Do the calculation. This is equal to 0.94 Vn. So I found the relation between VGS and Vn. Now, let's apply KCL here. Okay, let's apply KCL here. So KCL, we call this is node 1. KCL at 1. So all currents, assume them are leaving. So we will have V out over RD plus V out over RL plus GM VGS is equal to 0. Now, remember, I want to find the gain V out over Vn. By the way, this is not true. It has to be V out over Vn, not Vn over V out. So that's what I want. So I want to have the whole equation either in terms of V out or in terms of Vn. Now, this side is all V out. So I need to convert this to Vn. VGS has been already converted. So this is equal to V out 1 over RD plus 1 over RL equal to minus GM, and this is equal to 0.94 Vn. Perfect. So the only difference now, or the only thing that I am really interested in is to find GM. But we know that your GM from the previous formula we discussed at the beginning of today's lecture is equal to K times VGS minus VT. And these values, remember, it comes from what? From the DC analysis. So this is equal to 4. Your VGS is equal to 1.5 minus 1. So this is equal to 2 milliamp per volt. So I know now basically my GM. I know everything. I know RD, I know RL, I know everything. So basically here my V out over Vn will equal to minus GM times 0.94, okay, divided by 1 over RD plus 1 over RL. everything is there. So this is minus. GM is equal to 2 times 10 to the minus 3 times 0.94 divided by 1 over RD is basically the resistance RD, which is given to us as 18 kilo ohm. We found that, plus RL 1 over 100 kilo ohm. Remember, we found RD before, at the beginning in the DC bias, we found RD equal to 18 kilo ohms. So this is from the DC bias. This is, I always say that the AC analysis is based actually on the DC bias. So now we have all the values. So when you do the calculations, you will find this equal to minus 31.3, and that is the voltage gain. So this is how we deal with a typical question in the AC analysis. We start with DC analysis and then we move to the AC analysis.